Hello everyone, in this video we will be discussing an important topic in communication principle, which is generation and demodulation. These two processes are the foundation of how information such as a voice, music and data can be transmitted over long distance using communication systems. To understand modulation, imagine this situation. Imagine trying to throw a sheet of paper to your friend who is 5 miles away. No matter how hard you throw it, the paper will not go far. Air resistance stops it almost immediately. The sheet of paper represents our voice or message, also known as our baseband signals. Baseband signals are low frequency signals and they do not have enough energy to travel far. If we try to transmit our voice directly as a radio wave, it will not reach long distance efficiently. Now imagine wrapping the sheet of paper around a heavy rock and throwing it. The rock travels far and fast. In communication system, the paper is the message signal and the rock is the carrier wave, which is a high frequency signal. Modulation is a process of placing or piggybacking an information signal onto a high frequency carrier wave. We do this by modifying the amplitude, frequency or phase of the carrier. What is demodulation? Once the rock reaches your friends, they do not care about the rock itself, they want the paper inside. This is where demodulation comes in. Demodulation is the reverse process of modulation. It removes the high frequency carrier wave to recover the original message such as voice, music or data. The goal of demodulation is to separate the messenger, which is the carrier, from the message, the baseband. In amplitude modulation, we change the strength or amplitude of the carrier wave to follow the pattern of the message signals. When the voice signal becomes stronger, the carrier amplitude increases. When the voice signal becomes weaker, the carrier amplitude decreases. AM is generated using multiplier circuit that mix the audio signal with the carrier wave. At the receiver, the simplest method is an envelope detector. A diode acts like a one-way valve. A capacitor smooths out the high-frequency carrier. The remaining signal is the envelope, which is the original signal. AM is simple, low cost, but the signal is fragile and easily affected by noise. Next, in frequency modulation, the frequency of the carrier wave changes according to the message signals. When the audio signal increases, the carrier frequency increases. When the audio signal decreases, the carrier frequency decreases. The amplitude remains constant. FM uses a voltage control oscillator or VCO. The input voltage from the audio signal controls the oscillation frequency. While FM demodulation uses a phase lock loop PLL or a slope detector. This circuit detects frequency change and converts them back into the voltage change. FM is very resilient to noise. Since noise mainly affects amplitude, FM ignores it because it only responds to frequency change. Now let's move on to the phase modulation, also known as PM. In phase modulation, we change the phase or the timing of the carrier wave. Instead of changing the amplitude or frequency, the carrier wave is shifted slightly forward or backward in time based on the message signals. When the message signal increases, the phase of the carrier shifts in one direction, and when the message signal decreases, the phase shifts in the opposite direction. For the generation process, a constant frequency carrier signal is passed through a variable phase shifter. The phase shifter is controlled by the audio signal, which determines how much the phase of the carrier is shifted. At the receiver, demodulation usually requires a synchronous detector. This detector compares the phase of the received signal with a local reference signal to recover the original message. PM have a good noise immunity with phase-based information encoding, but requires wider bandwidth and more complex receiver design compared to AM and often FM. Now let's compare AM, FM and PM in terms of bandwidth, noise performance and system complexity. So first, For amplitude modulation, AM has a low bandwidth requirement, making it very efficient in terms of spectrum use. It only requires twice the message frequency. However, AM has poor noise performance. Most electronic noise such as lightning or electrical motor appear as sudden change in amplitude. Since AM carry information in amplitude, the receiver detects this noise directly. In terms of complexity, AM systems are very simple, often using only a diode detector. Next, let's look at frequency modulation. FM requires a much wider bandwidth. In theory, the bandwidth is infinite, but in practice, it is limited to acceptable range. The main advantage of FM is its excellent noise immunity. FM receivers are designed to ignore amplitude change and only respond to frequency variation. This also uses a feature called the capture effect, where the stronger signal completely suppress weaker signals. In terms of complexity, FM systems are moderately complex as they require tuned circuit or phase lock loop. Finally, for phase modulation, PM also requires a wide bandwidth similar to FM. The wider bandwidth helps improve noise resistance. The noise performance of PM is better than AM, but achieving performance similar to FM usually requires more complex hardware. Overall, PM systems are more complex than AM and can be comparable or slightly more complex than FM, depending on the design. Now let's discuss recent advancement in communication system. One of the most important development is software-defined radio or SDR. In the past, radio systems required different physical circuits for AM, FM, and PM. Today, SDR replaces most of this hardware with a software. A high-speed digital processor converts incoming radio wave directly into digital data. The demodulation process is then performed using software algorithm. Because of this, a single low-cost USB SDR device costing around $30 can receive AM, FM, PM, satellite signals, and even digital television. This technology has made radio engineering more accessible, allowing students to track aircraft using ADS-B or receive weather satellite image without expensive equipment. There are also several misconceptions related to radio communication. One common misconception is that living near a radio tower causes cancer. In reality, radio waves are non-ionizing radiation. They do not have enough energy to damage DNA or cause cancer like X-ray. The main safety concern with the radio transmitter is heated, such as radio frequency burn that can occur if someone touches a high-power antenna. Another misconception is that low-power FM broadcasting is legal. This is not true. Even low-power transmitter can produce harmonic signal that interfere with the emergency communication frequencies, such as an aviation radio bands. This is why strict licensing regulation exists, not to control content, but to protect critical communication system. In conclusion, modulation allows information to be transmitted over long distance using high-frequency carrier wave, while demodulation recovers the original signal at the receiver. Each modulation technique, AM, FM, and PM, has its own advantage and limitation in terms of bandwidth, noise performance, and complexity. With modern technologies such as software-defined radio, communication systems have become more flexible, affordable, and accessible. Thank you for watching. That concludes our presentation on generation and demodulation.